Right, so I'm going to do some revision for structure and bonding. We've already done lots of revision of structure and bonding, and there's lots of information already in your booklet. But what I can't really put in your booklet is dot cross diagrams, and there is one on the paper, so we're going to go through them now. The first one we're going to do is Cl2. Okay, so 2 chlorine atoms bonded together. Chlorine's in group 7, so I've drawn each chlorine with 7 electrons in its outer shell. Chlorine has got 7. But it wants 8. So chlorine wants to gain 1 electron. And if chlorine wants to gain 1 electron, then chlorine will share 1 electron. So to draw that they are sharing, I'm going to draw the 2 chlorines, and I'm going to draw them overlapping. Okay, I've got 7 dots to draw in total. All of this area in the center represents electrons that are being shared. The area on the outside represents electrons that are not being shared. So I can see here that chlorine wants to gain 1 electron, which means it will share 1 electron. So I'm going to put 1 electron in the shared space. The other 6 electrons I draw around the outside. They are not being shared. For this chlorine, it's exactly the same. I draw 1 in the shared space. I draw 6 on the outside. Okay? Check at the end that you've done this right. Each atom should have 8 electrons. So chlorine now has 2, 4, 6, 8. This chlorine has 2, 4, 6, 8. You must have an even number of electrons in the shared space. Okay, so 2, 4, 6. Okay, you can't have an uneven number in the shared space. Okay, and the other check that you're going to do is that you haven't drawn too many dots or too many crosses. Okay, chlorine's in group 7, 7 electrons in its outer shell. I should only have 7 dots in my diagram. I should only have 7 crosses in my diagram. So 14 electrons in total. Make sure you haven't drawn too many. The next one I'm going to do is HCl, okay? So hydrogen's got only 1 electron, and it's in the very first shell. So you need to remember that the first shell can only hold 2 electrons. Hydrogen has 1. If it gains 1 more electron, it will have 2 electrons in the first shell, which is a full shell. So if it will gain 1, which means hydrogen will share 1. Chlorine we've seen already, it's in group 7. It will gain 1 to have 8 electrons, which means it's going to share 1 electron. Again, to show that they are sharing, I'm drawing their outer electron shells overlapping. So note that I'm only drawing chlorine's outer electrons, okay? Chlorine's got 17 electrons in total. I'm just not drawing all of them. I'm only drawing the outer shells because they're the only ones that are involved in bonding, okay? So hydrogen wants to gain 1 electron. That means it will share 1. So it's only got 1 electron and it's going to share it. There's no electrons to draw on the outside. There's only 1 dot, and I've drawn it here in the center. Chlorine wants to gain 1, so it will share 1. The other 6 electrons it will keep to itself on the outside, okay? I've drawn 1 dot. For hydrogen, I've drawn 7 crosses, so I haven't drawn too many. I've got an even number of electrons in the shared space. Chlorine has 2, 4, 6, 8 electrons, so a full outer shell. Hydrogen's got 2 electrons, which is all it needs for a full outer shell. Okay, I'm going to do one more with you, and then I'm going to get you to do some by yourself. So CH4. The above 2 examples, I only had 2 atoms, so 2 chlorines and then a hydrogen and a chlorine. But in this formula, I can see I've got 5 atoms. I've got 1 carbon and I've got 4 hydrogens. Okay, when I'm drawing this, I'm going to draw carbon in the center because that's the element I've only got 1 of. I'm going to put that in the center, and I'm going to put the 4 hydrogens around carbon. Now, make sure that when you are drawing your hydrogens in, that the hydrogen shells don't overlap with each other. So the hydrogen and carbon electron shells should overlap, but no hydrogen outer shells should overlap, okay? If I look back at carbon, I can see it's in group 4, so it's got 4 electrons in its outer shell. It wants to have 8, which means it needs to gain 4 electrons. If it wants to gain 4, it will share 4. Hydrogen we've seen already. It wants to gain 1, which means it will share 1. Okay, I'm going to do all of my hydrogens first. Hydrogen wants to gain 1, so it will share 1. So this hydrogen will share its only electron with carbon, and I draw it in the center. This hydrogen will share its only electron with carbon. This hydrogen will share its only electron. This hydrogen will share its only electron. Okay, hydrogen only has one and will always share its only electron. So you should never have electrons drawn on the outside for hydrogen. It always shares its only electron. Okay, and I've drawn one cross for each hydrogen, 4 hydrogens in total, 4 crosses in total. Carbon has got 4 electrons, so I need to draw 4 dots. I can see that it wants to gain 4, which means it will share 4. Carbon is going to share all of its electrons. And unlike in the above examples, I now have 4 different sharing spaces, and carbon has got 4 electrons to share. So what carbon will do is it will share 1 electron with each hydrogen. So it's sharing all 4 of its electrons, so there's none that it keeps to itself, and it shares 1 with each hydrogen. Okay, this means carbon ends up with 2, 4, 6, 8 electrons of full outer shell. Each hydrogen has 2, so carbon and hydrogen are both happy. I've got an even number of electrons in each of my shared spaces. I've got 2 in each shared space, okay? And I've only drawn 4 dots in total, and I've only drawn 4 crosses, okay? So 1 for each of the hydrogens. So I haven't drawn any extra dots. I haven't drawn any extra crosses, okay? Have a go, if you're okay with this, have a go at these 4 examples yourself and press play when you're ready to see the answers. If you're not okay, then stay with me. I'm going to go through them all anyway, but have a go by yourself if you think you know how to do this, okay? So press pause and then have a go and then press play again. Okay, I'm going to continue on. So NH3, I've got 1 nitrogen and I've got 3 hydrogens. Again, nitrogen's by itself, so I'm going to put nitrogen in the middle. And I'm going to put the 3 hydrogens around nitrogen. I'm going to make sure that those hydrogen shells don't overlap with each other. Okay, so I've got 3 hydrogens around my nitrogen. Nitrogen's in group 5, so I've drawn 5 electrons in its outer shell. It's got 5, it wants 8. That means it will gain 3 electrons. And if it wants to gain 3, then it will share 3. Hydrogen, we've seen already, wants to share 1 electron. Okay. So hydrogen's only got 1 electron and it will share it. So I'm going to fill in my hydrogens first. So 1 cross in there, 1 cross in here, and a cross in here. Hydrogen doesn't have any other electrons, so you should never have electrons drawn on the outside for hydrogen. It's sharing its only electron. So I've drawn my 3 crosses in because I've got 3 hydrogens, 1 electron for each hydrogen. Now I have a look at nitrogen. It's got 5 electrons. I've got 5 dots to draw, but it's only going to share 3 of them. Okay? You've got 3 sharing spaces and it's got 3 electrons that it wants to share. So I'm going to put 1 dot in each of the sharing spaces. Okay, so that's 3 dots drawn, but I've got 5 in total. So I'm going to put 2 dots on the outside that are not being shared. So it's sharing 3 electrons. It keeps 2 to itself. Okay, this means in total I've got 2, 4, 6, 8 electrons for nitrogen. I've got an even number of electrons in each of my shared spaces. I've got 5 dots drawn in total, and I've got 3 crosses, 1 for each hydrogen. So that's what NH3 should look like, okay? If we look here at H2O, you've got 2 hydrogens and 1 oxygen. So oxygen's only got 1, so I'm going to put it in the center, and I'm going to put a hydrogen on each side. I've seen hydrogen already. I know it only has 1 electron, and I know it's going to share it. So I'm going to put hydrogen's cross in here, and hydrogen's cross in here, and I'm not going to draw any electrons on the outside for hydrogen. Now we need to have a look at oxygen. Okay, oxygen has got 6 electrons in total. It wants to have 8, which means it will gain 2 electrons, and if it's going to gain 2, then it will share 2. Okay, it's got 2 electrons to share, and it's got 2 sharing spaces, so it's going to put 1 electron in each sharing space. Okay, I've only drawn 2 dots. I've got 6 in total, so I'm going to put the other 4 on the outside. They are not being shared. So if I do my check, oxygen has 2, 4, 6, 8 electrons. There's an even number of electrons in each shared space. I've drawn 6 dots for oxygen. It's in group 6. And I've drawn 2 crosses, 1 for each hydrogen. So I've drawn the correct number of electrons. Next up, I've got O2, okay, which is 2 oxygens joined together. So I'm going to draw my circles overlapping, 2 oxygens joined together, okay? We've seen above that oxygen is in group 6. It wants to gain 2, so it will share 2. So both oxygens want to share 2 electrons, all right? if I come down here, this oxygen on the left, okay, there's only got one sharing space, okay? It's got 2 electrons that it wants to share, but there's only one sharing space. That means I need to put both of its electrons into the same sharing space, 1 and 2. The other 4 electrons it has, it doesn't share, and I draw them anywhere on the outside. For the next oxygen, it's the same situation. It wants to share 2 electrons. It's only got one sharing space. So it has to put both of its electrons into the same sharing space. The other 4 electrons, it keeps to itself. Okay, so what this means is this oxygen has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8 electrons. I've only drawn 6 dots and 6 crosses. And in the center, okay, I know it's more electrons than we've had in a sharing space before, but the rule is that it just has to be an even number of electrons. We've always had 2, now we've got 4, but that's fine, okay? 4 is an even number, it's fine to have 4 electrons in the center. And what this would look like, okay, each pair of electrons is one covalent bond. You've now got 2 pairs of electrons, so instead of just having one bond between the oxygen atoms, you've actually got 2. Okay, you've got a double bond between the oxygen atoms. Each bond is 1 pair of electrons, and you've got 2 pairs. Okay, very last example, nitrogen. We've seen nitrogen already. It wants to gain 3 electrons, which means it will share 3 electrons. So I've got 2 nitrogens overlapping. Okay, it wants to share 3 electrons. It's only got one sharing space, which means it needs to put all of its electrons into that same sharing space. So all 3 dots go into that one sharing space. That leaves nitrogen with 2 electrons that it's not going to share that go on the outside. The next nitrogen's in the same situation. It wants to share 3 electrons. It's only got access to one sharing space, and it's going to put all 3 electrons into the same sharing space. It keeps 2 to itself. Each nitrogen now has 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. I've only drawn 5 dots and 5 crosses to represent that each nitrogen has 5 electrons in their outer shell. And in the center, I now have 6 electrons. But again, it's fine to have 6. 6 is an even number, so you can have 6 in the center. And I said that each pair of electrons represents one bond. Okay, so now you've got 3 pairs of electrons. So between nitrogens, you're actually going to have a triple bond. You're going to have 3 covalent bonds between 2 nitrogen atoms. It's a triple covalent bond. Okay, they are your dot cross diagrams. You do need to be able to do them. I think these are pretty much the only ones you need to be able to draw. So if you're okay with all these, then you should be fine for your exam. So all of the structures that we have drawn are all examples of molecules. They are all examples of simple molecules. How do I know? How do I know that these are all simple molecules? Okay, well, to be a simple molecule, you have to fulfill 2 criteria. You must be covalent, okay? And you should know that covalent is between non-metals. So if you look at all of the examples that I've drawn, you've got non-metals. There are no metals in here at all. So all of these bonds are covalent bonds. So each of these is covalently bonded, non-metals. The other criteria it must fulfill to be a simple molecule is you have to be able to write a chemical formula. In order to write a chemical formula, you need to know how many atoms that you have got. So if I look at this, I've got 2 chlorines, okay, Cl2. Here I've got 1 hydrogen and 1 chlorine, so that's HCl. Here I've got 1 carbon and 4 hydrogens, CH4. Here I've got 1 nitrogen and 3 hydrogens, NH3. Here I've got 2 hydrogens and an oxygen, H2O. Here I've got 2 oxygens, O2, 2 nitrogens, N2. Okay, in each case, I was able to write a formula, and I could do that because I know exactly how many atoms there are. Okay, in other covalent structures, so giant covalent, you don't know how many atoms there are. There are billions, and you can't write a formula for it. But for simple molecules, you can write a formula because you know how many atoms you've got. Okay, these are all examples of simple molecules, and you need to know the properties of simple molecules in terms of melting and boiling points, in terms of conducting electricity. Okay, so you need to know that simple molecules, okay, that Clue is in the word molecule, okay? If you're talking about melting and boiling points, you are talking about forces. How or what strength are the forces that hold the particles together in a solid, a liquid, and a gas, okay? Simple molecules are held together by intermolecular forces, okay? That word intermolecular literally means between molecules. So the force that exists between molecules are intermolecular forces, and they are weak. Because you've got weak forces holding the molecules together, they are going to have low boiling points, okay? And they are going to be gases at room temperature. Some of them will be liquids, okay, water will be a liquid, but most of them will be gases at room temperature, okay? And all simple molecules are the same, okay? They're held together by intermolecular forces. Those forces are weak. Because those forces are weak, you don't need a lot of energy to pull those molecules apart. If you don't need a lot of energy, you don't need a lot of heat, so the boiling point is going to be low, and they are going to be gases, okay? Other property that you need to know, okay, low boiling points. Also, they will then obviously have low melting points. Low boiling points, low melting points. When I say low, I'm talking about, in the minus numbers, okay? So to melt chlorine is like, minus 100 degrees Celsius is required to melt it, okay? Really, really low temperatures in the minuses to melt and to boil these structures. The other property you need to know is in terms of conducting electricity. You should hopefully remember that in order for something to conduct electricity, it must have charged particles of some description, some sort of charged particle, and those charged particles must be free to move. And there are two types of charged particles that we've come across when we've been looking at conducting electricity. We have looked at ions, and we have looked at delocalized electrons, okay? Simple molecules do not have ions, okay? In order to form ions, an atom needs to lose or gain electrons. In all of these examples, they are sharing. Okay, sharing is not the same as losing or gaining. Sharing means you do not form ions. Okay, so there are no ions whatsoever in simple molecules. Okay, your simple molecules also do not have delocalized electrons. Okay, they do not have them, which means they don't have any free moving charged particles. None of your small molecules are going to conduct electricity because they don't have any free moving charged particles. Okay, so very, very poor conductors of electricity. Simple molecules, low melting and boiling points, do not conduct electricity. Okay, the other example of covalent structure, which I briefly mentioned a second ago, was giant covalent. Okay, and there's only certain examples of giant covalent you need to know. You need to know diamond, and you need to know graphite. Okay, diamond and graphite, they're both made of carbon. Carbon's a non-metal, so you've got lots and lots of non-metal carbon atoms joined together by strong covalent bonds. Okay, they don't form molecules because you don't know how many atoms you've got. They form these giant structures, and we say that they are giant covalent and they are not simple molecular, okay? Because they are not simple molecular, we are not going to be talking about intermolecular forces. We are just going to be talking about the covalent bonds, and the covalent bonds are strong. And if they are strong bonds, then they are going to have high melting points, and they're going to be solids, okay? They're going to be strong solids with high melting points because of all of the strong covalent bonds. Lots of energy is going to be required to break them, okay? They don't conduct electricity. Typically, giant covalent substances typically don't conduct electricity. But there is one exception, okay? Graphite is an exception, because graphite has one of the charged particles. It's got delocalized electrons. So if you remember, in graphite, carbon only forms 3 bonds instead of 4, which means it has delocalized electrons. Each carbon atom has an extra electron that's not involved in bonding. Delocalized electrons means graphite can conduct electricity, okay? But that's only an exception. Most giant covalents, diamond included, will not conduct electricity, okay? They've all got strong covalent bonds. They've all got high melting points. They'll all be solids, okay? but graphite is an exception. It will conduct electricity because of its delocalized electrons. Other giant covalent structures won't conduct electricity, okay? One more note, okay, graphite, you'll remember graphite had layers. It had lots of different layers, and because it had all of these layers, it was soft and slippery because the layers could slide over each other. One layer of graphite is called graphene. Okay, so graphite is lots and lots of layers, but graphene is just one single layer. Graphene has all of the same properties of graphite, okay? Graphene is made of carbon. Those carbon atoms are held together by strong covalent bonds, so graphene has a high melting point, okay? Graphene, the carbon atoms in graphene only have 3 bonds, just like they do in graphite, which means graphene can conduct electricity. So graphene is going to have all of the same properties as graphite. It's just that it's one layer instead of lots of layers. The only thing you're not going to say for graphene is you're not going to talk about graphene being soft and slippery. Because if you remember, in graphite, it was soft and slippery because the layers could slide over each other. Graphene is just one layer. Therefore, it's not going to be soft and slippery. I have given you practice questions that I've already gotten you to do for homework. They were all here in your core info booklet. I would recommend being able to answer the key questions that I've given you and then doing the practice questions on structure and bonding to make sure that you are able to answer the questions on structure and bonding. Paying particular attention to the difference between giant covalent and simple molecular, and also being able to recognize what's giant covalent and what's simple molecular. So all of these little molecules here, they're all simple molecular. I can write a formula for them. Your examples of giant covalent are diamond, graphite, and then one layer of graphite, graphene, that's also going to be giant covalent. Just to note, we did mention 2 other types of structures, allotropes of carbons, fullerenes and polymers. Okay, they are simple molecular as well. Okay, they are simple molecules. So you'll remember fullerenes are spherical in shape. Yes, they're spherical. And we can say that because they're spheres, the molecules roll over each other and they're soft and slippery. Okay, that's a unique property of fullerenes, but they are also simple molecular, which means all of the properties we learned about simple molecular apply to fullerenes. Each individual sphere is called a molecule, and those spheres are attracted to each other by intermolecular forces that are weak. So fullerenes have low boiling points. Fullerenes do not have charged particles. They don't have ions. They don't have electrons. Delocalized electrons. So fullerenes do not conduct electricity. So fullerenes, their unique feature is that they're spherical. Okay, but they are simple molecules, and all of these properties we learned for simple molecules will also apply for fullerenes. Polymers are technically simple molecules. Their properties are a little bit harder to predict. It depends on the size of the polymer, but don't worry about the properties of polymers. Do worry about the properties of fullerenes, the properties of simple molecules in general, and the properties of giant covalent structures in general.